Okay, welcome everybody to the fourth lecture of this year of the Shanghai lectures. Today we have a pleasure to have Christoph Pomorski from the University College Dublin, who will give a guest lecture on quantum computation and the possibility which is now in the future, but it seems to be real, of applying quantum computing to at least some problem in AI. As usual, and I will first give one of the lectures in the main thread, introductory thread of our textbook, which is how the body shapes the way we think. And then we will have a short break to arrange the guest lectures, and Christoph Pomorski will give us a presentation on quantum computing. Basically. You may know that after being considered a speculative topic for many years, now there have been, in the last few years, really, there has been significant progress in quantum computing, and but Christoph will give us more detail. And you may know that in the past, for example, Roger Penrose suggested that the brain itself is difficult to understand if you don't think that there is some kind of quantum computation ongoing. I'm not completely in agreement with that, because it could be a not necessary, you know, the concept of the Occam's razor. You should introduce as little complications as possible. And so if we don't need, we should not consider that there is a quantum computation there. On the other hand, it's true that in recent years it has been shown that even in photosynthesis, in plant leaf, there is some quantum process ongoing. So maybe the reality, as usual, is a bit more nuanced. So the topic of today is the role of evolution. The topic of the general lecture is the role of evolution in the building of cognition, in the creation of cognition. I start from where we were last time, you know, because I would say that in one line, the idea coming from the second lecture was it's not so clear how we should define intelligence, and it's also probably not necessary. What we should study in both natural systems, so in nature, and in artificial systems, is how to simulate or recreate behaviors that we think are interesting and that involve information processing, perception, and interaction with the environment. This is, by the way, also a very engineering, so an approach that engineers like. Right? So we have seen but in the meaning that actually typically engineers, when they basically, it's common in the engineering community not having a particular philosophical point of view, and I think this is a mistake. But as engineers have, together with laymen and laywomen and with everybody doing something during the day, in daily life activity, to have very few assumptions, not to be kind of skeptical. And so this is, if you have that attitude, you stay away from general definitions and you try to solve individual problems. This, in the case of intelligence, seems to be also justified by a more general consideration, the fact that we don't have a real idea what is it. An example that we saw last time was the work by Olko Cruz on ants, to understand how ants can walk, for example. What has been shown in empirical, so experimentally, so what has been actually checked in nature and that is shown to work is that the terrain has a basic, has a key role in the way that ants work. So we have seen the Foyt experiment by Simon on the ant on the beach, and you by imagining, you understand that depending on how the beach terrain is done, you will have different paths that may look to an observer very complex, while in practice they just come out from simple reactive behaviors. What Olko Cruz has proven, has discovered in ants, is that this is actually what happens in real ants. So ants have a connection, they have a simple control in the hinge of a leg, which is, by the way, deformable, and this has a role for sure. And the connection between the simple neural circuits here and that here is given by the terrain, by the reaction of the terrain. So basically, the working behavior of ants is emergent, and this is interesting. We have seen that a way to put together these ideas, so to give a model of this in terms of embodied intelligence, is to introduce in between the task, the environment, and the controller, which is the mainstream approach. No? The humanoids robots of the Grand Challenge, of the DARPA Grand Challenge, robotics challenge, are built without this blue intermediate layer. So this is why I think that for two reasons. One is a kind of philosophical legacy of Cartesianism. You know that René Descartes divided, was a very important philosopher, a European philosopher of the 17th century, gave, and actually is one of those philosophers that more or less defined what we think as Western thinking, right? And actually, one of the ideas of Descartes, one important idea which has a lasting effect, was that body and mind are two completely different things. The body is a machine, like a clock, or a clockwork, while the mind is something non-material, non-embodied, connected, so more or less living in the brain of the people. And this idea is probably still having a lasting, so we still have this idea not openly discussed, and first, and also if you want to build a robot, it's easier to work in this way, because so you have a mechanical model of a robot. By the way, we on modeling in the last lecture, we will have a very insightful guest lecture on how we can model the methods that we have to model physical systems, whether they are natural or whether they are not, or mixture of the two. But if you want to build a robot, there is a way to do it, is to have a programming the intelligence on a computer and connecting the computer to a physical body that you can model. So I think that there are two reasons. One is that philosophically we are still, when we don't think about it, we still think that we have a body and the mind, that they are not the same thing. And then it's from the practical standpoint, it's also natural to work in this way, because so you have a clean model of the physics and you have your program. And these are, this is the only problem with this is that this doesn't seem to be what happens in nature, because in the example of ants working, and you know that the story about ant colonies is that the single ant is stupid, but the colony as a whole is intelligent, adaptive. So if you would like to you remember the discussion on what is intelligence, the ant colonies are able to adapt to their environment, they learn from the environment, they identify food sources, protect themselves. So ant colonies as a whole are something that sometimes is called superorganisms. So they have a form of a set of intelligent behaviors by themselves. This is also true for cities or for human societies to a certain extent, because I'm maybe going too far, but we have our individual objectives, but then our behavior as a society, now as a global society, as humankind, is something which somehow transcends what we want to do. So there are unexpected effects of what we do, and we know that as the states, or humankind as a whole are much more powerful than a single individual. So the strength of humans is that we can cooperate not even more in millions of people, but in billions of people, for the better, so for the better or for the worse. So going back to this field, so this blue layer is only present in some extent. And the point is that in nature, for example, in ants, in stupid ants, by the way, a single ant, it's considered as a robot, is much better, much more intelligent than any robot competing in the DARPA challenge, the stupid unit of an ant colony. But they exploit the body morphology, and even they close the loop of sensory motor perception in the environment. So this means that we need, and we will come, in the next lecture we will talk about more in detail about morphological computation, self-organization of behaviors and things like that. And we will see how this can be implemented in a robot. We are at the beginning, but we see that at least in terms of intuition, this is somehow convincing, because as in the example that I do all the times, but I repeat because I think it is useful. the mechatronic paradigm approach to grasping is reconstructing the image, reconstructing the position of the hand, calculating a trajectory by planning, and then moving all the joints in the arm until I reach more or less, I get close, and then I calculate again for every finger the trajectory to follow to grasp the pen. What happens in nature, which is true for walking, and it's true also for grasping, is that more or less I move the arm here, and then I let it fall close to where. And when I'm close, I don't calculate a lot. I just give a number, an instruction to close. And this is what is managed by, means that a lot of the approach, there is the reaching movement, but also the grasping itself, is managed by the musculoskeletal structure of my arm. This is something that we understand, that is true in biomechanics, but it's not that. So now I try to because if now you see, if you look, and then we see this. This is, if you wish, this is a simple version of a behavior of an ant colony. This is a huge number of birds able to behave in a very organized and intelligent way. What I would say, this has been modeled, and now you can also see it into, for example, in video games. Like I wasn't able to find someone willing to. Just a minute. Because then you have these other kind of example. So this is a simple process happening in a human cell, and is a simulation developed by Harvard biologists, and it is based on what you know. If you want, what we knew 3-5 years ago on this kind of phenomena. And you see that it's really, so this is a simple protein building process. You see that the complexity, it's really impressive. But this is not the main point. The main point is that all these complex behaviors are the consequence of are emerging processes from the interactions of literally billions of small parts, and this behavior is stochastic in nature, so it's not deterministic. This is really just a minute. So this is really the opposite of what we do. This is just a minute. Now, so what I mean here is that we see that in nature we have this this characteristic. So I tell it every time, but it's probably one of the more important things to remember. So we so far, I would say in the mainstream, all our smart system, intelligent robots are based on the idea that I have a top-down control. So I have a program which coordinates everything and go down to control a body. These systems are more and more complex, but are still simple if compared to a single ant. So if you look at nature, we see that the principle of organization are completely different. So it's not deterministic, it's stochastic. So act, interact. There are many parts, and the intelligent, at least the behaviors that we are interested in, for example, coordination of a swarm of birds, or fine-tuning, or biochemical processes inside living bodies, is emergent. So loosely coupled networks, massive networks, emergent processes. So it's completely different thing. Another important characteristic is that this double function. So part of intelligent behaviors doesn't come from reasoning, but from the structure of my arm, of my legs, if I'm walking. And this, for some reason, give... so if you think about this, make it much easier to... so you have a lower computational burden. So because if I don't need to calculate all the trajectories in the joint space for all the joints of my body, and my body has very complex joint. This is not a rotational joint. This is a very complex surface in 3D, and it even deformable. So this is something that is an engineer's nightmare. So why? But once I have this structure, I can do very well this kind of task, consuming little computation power and consuming little energy. I think I told you, I'll tell you again, one of the main characteristics in walking is that in fully actuated humanoid robots, you consume per meter, at the same speed, 20 times more energy than people do. And this it does, and this is really strange. But the reason is that so less energy, but also less computing power, because I don't need to do a lot of calculation. So it would be nice to be able to do that. Then there is another characteristic, because a mistake, let's say, that we may do when you, but probably we, as a community, we did for many years, is that when you talk about artificial general intelligence, when you think of a Turing test, so the Turing test is supposed to show that a computer program is undistinguishable from an adult. I would think that we think an adult human. So you remember that when I quoted the Loebner Prize that was given to a program that was confused with a 12-year-old boy. Well, I don't know, because a 12-year-old boy is so I told you already, so it was a bit confusing. But the idea is that we think about for example, even in my example of the grasping, well, the people doing this grasping was not able to do this when I was 6 months old. So there is also this characteristic. So the way learning occurs in natural systems, because again, these lectures are about intelligence in artificial and intelligence in natural systems. And what we see in natural systems is that we have at least 3 levels of learning. And all these levels are in the line of a morphological computation, because they think to the you have 3 stages now, from the top to the low level, to the bottom of this slide. At the top, I have so I know how to manage this pen, but I don't know very well how to use this remote controller of a camera. So here and now, I apply procedures that are very similar to artificial procedures like reinforcement learning to understand how it works and to make practice. So you may have noticed, for example, that I still need to do some practice on the whole video conference system. And this is the short-term learning. But I do this when I already know very well how to manage objects. I know how to play tennis and table tennis. So I know how to do a lot of tasks, because I am at a point in my lifetime. Anyway, I need to learn how to use new equipment, even a new phone. Right? And this is one level, but this is not all the story, because as I told you before, we were not born like science fiction, already adults. We had a long process where we learned to move, to have an idea of the space around us, to reach to grasp objects, to recognize the voice of our mom or whoever was taking care of us. And this took an enormous amount of time. So just to be able to join the university, you spend learning in a structural way at school and in an unstructured way out of school, almost 20 years. And then you start to enter in more detailed things. But even when you are in primary school, you already had several years of learning before. And this learning had 2 characteristics. One is that it started almost from scratch. So actually it's still open. So we don't know exactly from what this scratch means exactly. Probably some structure, some cognitive structure are already built in the brain, but we don't know exactly what. But then we learned a lot of things. So the first thing was we learned more or less from scratch. This is not true for robots. We inject the program. It was not true until recently, because you can implement a learning system on a robot, and this learning system is typically in what I've called the short term, here and now. Then this is the other thing is that there is a coevolution of the arm and the brain structure in charge of controlling the arm. Because first you have a very small, very soft arm, not able to do precise movements, and you have very simple brain structure controlling the arm. And then while the arm grows, also your cognitive structure grows. And this continues until 25, when you are 25 years old, when the plaques, the skeleton structure of the cranial structures get fixed, finally fixed. So actually you should study more, the more that you can before you are 25, because before 25 you still can enlarge the school dimensions. When they are fixed, you at least the space for your computing, personal computing environment is limited. But it gets fixed at 25. So very, very late in time. Then, and this is development. So we are facing learning in short term and development. But a baby learning to talk or any language, or learning to grasp objects or to walk alone is already a human baby. But to reach this level, you have another more long-term learning process, which is the evolution itself. So actually, it may take, I don't know, half an hour to learn how to use the video conferencing system, to learn to a certain extent. And then you practice and you improve. Same for tennis or whatever game. Then it takes 25 years to become an adult human. But it takes billions of years to have a human of evolution. So actually, and this is again evolution of information processing and cognitive processing together with evolution of different body sets. So ants, birds, and humans are different. They all have some kind of, for sure, information processing, but also some kind of adaptation and intelligence behavior. And this took literally ages. So the important thing is that evolution in nature plays an important role. By the way, you may know that there is now, as usual, I tend to, there is a niche conference that is extremely interesting, which is the Evo conference, no? The ICDL. Because there is a niche community of researchers in AI which are actually trying to simulate the evolution and the development to achieve intelligent behaviors, and this is very, very sensitive. Another aspect is you also understand why we don't do this all the time, because simulating the coevolution of the body and the control structure of the body technically is extremely difficult. So but we can do in simulation. You will see. You can check an old guest lecture by Minoru Asada from the Osaka University, who actually managed a huge Japanese project where they tried to simulate mixing prototypes at different ages and simulation, the process of development of a baby. And and then the last lecture will be by Josh Bongard, Professor Bongard from the University of Vermont, will be about this in simulation. Not surprising, I told you about if you check this paper by Turing in 1951, you see that actually Turing himself was convinced that something like that was necessary. I don't read the whole thing, but it was insisting on development and learning. And here, but this I wanted to leave for next lectures. But actually, for the next lecture, the story is that so I need a way to connect physical, so physics dynamics to information process. I need anticipation, but we have seen in the first lecture that Aristotle was already aware of that. And this it needs to go, and you see, this is, if you think about this, this information self-structuring, so the model of Vetrolf, the schema of embodied intelligence from the article that I've shown at the very beginning, actually it's much more, going much deeper, because of all this, we have we can identify 3 time scales, and at all time scale we have this coevolution of body morphology and dynamics and information processes. And if you look at evolution, we have many kind of intelligent behaviors with very differentiated morphologies. So dogs are quite similar to us, but octopuses are very different. And octopuses show remarkable behaviors that we believe are intelligent. And then another thing, we go the other way around, because at the very beginning of AI in the 50s, people started from an approach where intelligence was basically the capability to understand and prove theorems. And then you have mundane tasks like walking or doing other things, which was an inferior activity. The paradox now is that we have theorem-proving algorithms, but we have still problems in interacting with the real world. This study by Lakoff-Núñez already in 2000, a book that I advise you to read, goes the other ways around, because they did, and recently Núñez did also some study with brain images that actually some very basic idea of mathematics. Also on this, if you check, there is a guest lecture, an old guest lecture by Núñez on this. Actually, the concept of limit. So what they did was recording mathematics professors explaining concept of analysis, of calculus, and for example, the limit, right? So what happens is that when you do the limit for x going to infinite, and you do this in the brain of the people giving the lecture on limits, the movement structure in the brain are activated. So actually, going to infinite for our deep brain is actually activating motion neurons. So the idea here by Núñez is that our mathematical understanding is grounded in our body experience. So it's actually the opposite. So because we started some almost 70 years ago, or even before, I would say, thinking that with the hard stuff, mathematical theorem proving is the real difficult thing, and all the other things that we do almost unconsciously all the day is trivial. After decades of study in AI and robotics, we know how to prove theorems automatically to a certain extent. Many theorems that would be very difficult for me to prove can be proved by an algorithm, especially the very long one. Those who have very long proofs. And while the rest of the things is extremely difficult. But then we discover that mathematics is a kind of, or we may think that, I'm in favor of it, is actually an abstraction of our body bodily experiences. So if you wanted to understand whatever it is, intelligence or different kind of intelligence, you should start from the body, not from the eye level of the brain. Of course, this is much more difficult. So I never want to say that it was a mistake starting from an approach not considering dual functions, so body morphology, interaction, and development, because it's with our current technology it's difficult to do. Also, this story of the time frames that in the previous, and then I think I can stop. Because it's more or less what I wanted to say today. Actually, as usual, it is an abstraction to say that there are three levels. So here and now, short term, development leading to the proper brain and body necessary to perform a function, and evolution leading to myriads of different bodies doing different things and performing different tasks. But this is a schema, so it's a simplification, because if you look here, we have different time scale, even in what I have called the short term. And if you look at this picture where you have time above, and we go from 1 millisecond to 1 million year, you see that we have the here and now, which is in the seconds, the minute, maybe the hour of a day. And then you have the development, which is in the years, of a tenth of years. And then you have the phylogenetic level, so the evolution, which is, well, it's not 1 million years, it's many millions of years. So one thing that you may want, so you may think that it's impossible. Well, it's not impossible, because not surprisingly, we have these things are studied, and for people interested, I also always suggest you to go to the textbook, but if you are interested, I can provide you some additional references, because as time passes, we have studies and models for all these things. So for the thermic mound, but also for how waving stadium form, and that could also be politically interesting. No? So how you can shape behaviors of people. So this, by the way, is one of the issues with Facebook, no? Because with Facebook, or in general social network platform, you have a lot of data, and this data can be used to fine-tune, to obtain the reactions so you have a kind of swarms. So we collectively in social networks, but also in physically embodied networks, for example, in Shanghai, we interact all the time like a swarm of birds. We have different levels. we have, this is a different discussion, but we also have a cultural evolution. No? So we don't see the way our parents saw the world. So every people have a different attitude, and as time passes, what is considered real and not real changes. And so it's really, but we are studying this. For example, if you look at this paper by Bettencourt and others, the origins of scaling in cities, you see that you can even model, for example, how a city will grow. And this is good, for example, for urban planning. Because, but this is really a long story, you know? But because we tend to think of history like we have a political institution driving the society. This is not the whole truth, because the society tends to evolve like a swarm of birds. And there are rules which are kind of physics, collective physics, that goes beyond the planning. Maybe just now we are starting to understand how you can somehow shape this kind of thing. I told you that something has been done, for example, by Josh Bongard, this in simulation. He has developed, he has shown, this stupid balls chains are robots evolving to push blocks. And this in simulation works. So it's difficult, but it's not impossible. So I think that since it's already late, so the carry-on message today is the importance of time frames and the fact that in this, so basically it's like to say that there are learning processes at different levels, and the main different levels are learning a specific skill, so here and now, hours or days or even years, no? Because you never finish to learn to play tennis, or table tennis, or whatever you like. And then you have the development, and it takes in humans 25 years to develop the brain structures and the body structure, and also what you have in your brain, because you also, in these 25 years, you don't just build a brain structure, you also build a lot of ideas of ways to understand the world. So, and second, so here now, development and evolution. And evolution is because a baby is already the end point of a learning process that on this planet lasted for billions of years, from tiny RNA chains self-duplicating in a very strange place, no? In a primordial ocean to us. So it took billions of years. So, and so this is what happens in nature, and we have seen that, for example, at least in simulation, but also in some project, we are starting to try to deconstruct this. We also have seen why what we are talking, what we are discussing next time is important, is at this point, it is necessary to have some model of about how the morphology of the body, the dynamics of the body, lead to interesting, intelligent behaviors. And for today, and for me, this today is what I wanted to just a minute, because I'm so since it's late, so please feel free to send me emails to if you have questions, in particular if you want to some additional reference with I think that so it's already a lot what you find in Rolf's and Josh Bush, but of course 10 years passed from them, from those times, and there are some additional references that weren't there for for obvious reason. No? So it was not so it was not done. It was done. So now it's my as told. So as told, we actually don't know. Actually, Roger Penrose did this hypothesis that looked at very strange at those times, and now it seems less. But actually, it's a fact that it's possible to have a quantum computer, and that this quantum computer, for example, simulated annealing, which is an optimization algorithm which is usually performed in supercomputer and now also GPUs, is something that on a quantum computer works better. So it was while to listen to Krzysztof Pomorski from the University College Dublin to learn something about quantum computer. And Chris is, I think, one of the few people who can tell us something about this topic. So, Chris, welcome.
Hello.
Hello. Yes, we hear you.
Can you hear me?
Yes, perfectly.
All right. So now I need to share the presentation, right?
Yes.
All right.
And
so
I think you are doing it already. Yes.
Yeah. Can you see the presentation?
No.
1 second.
I think you should open it before hitting share. Now I see your screen. You have shared your screen.
Yeah. So can you see the presentation?
No.
You don't see my presentation, or?
No, I can't. I see your screen, your desktop folder. So stop sharing. So open the presentation. Stop. So we are having a 5 minutes break.
Yeah. Well, 1 second.
So you should
all right.
Stop. So stop sharing whatever you are sharing now.
All right. 1 second. Stop sharing. Pause share, right? And resume sharing.
No, stop sharing and a new share. You should do a new share.
All right. Can you see now? Can you see?
I can't. So let me.
Okay.
No, take your time because we can take about 10 minutes. So we have a 10 minutes break now.
Okay, we have 10 minutes break, right?
Yes, and so we can experiment.
Okay.
So now I see you. I think you stopped to share. So if you have opened you should first open the presentation. Now you stop sharing because now I see you again without sharing. And then when you share in the screen, you should see your presentation. And then you share that. You click on the presentation, you share it.
Okay, so first, 1 second. Try to share. Can you help me? This one. Yeah. All right. And oh, yeah. This one.
Yes.
All right. Can you?
Yes, yes.
Can you see the whole? Is it fully visible, or is it 25% size?
It's a little smaller because I think you still have to put the full screen, right?
Right. 1 second. I'm just because I'm using the computer from. Yeah, I'm using university computer. I just discovered they didn't install Acrobat Reader, but right now it shall be installed. So I will try to open in Acrobat Reader, right?
Yes. No, take your time and please accept my apology. I tend to underestimate the difficulties, but I think it will take 5 minutes. And don't
25 minutes. All right, it's a very big subject, so it'll be hard, but still I will try. Okay, stop share.
Okay, yeah. No, it's a very big job, so thank you for enlightening us on this topic.
I will see how things will go in practice, but yeah, so yeah, I'm in Acrobat Reader right now. Okay, so, and now I supposed to
share yes, okay.
Full screen. Yeah. This one. Right. Sure. Which one? Okay, this would be maybe this one. All right, so how is visible now?
Perfect. Perfect.
All right.
So it was 5 minutes, huh? Yeah. Okay, so Chris,
shall I start?
Yes. So you may also... Okay.
All right, so welcome to everybody. My name is Chris Pomorski. I am postdoc at University College Dublin, a School of Electrical and Electronic Engineering. I have a background in electronics and also in physics. I did my PhD in Josephson Junction physics. And quite recently, I'm working on quantum computation and quantum artificial intelligence. So basically, I'm working right now on implementation of quantum computer in a CMOS technology. All right, so I will just give a very brief view of current existing trends, what I do, and I would just mention about perspectives related with quantum artificial intelligence. Okay, so you see my collaborators as co-authors of this presentation. So basically, at the very beginning, I would like to draw the picture. What's the difference between bit and qubit, which is a quantum bit. Then I would like to show that how to view computation as physical process. And then I will move to the concept of programmable matter, which basically the whole artificial intelligence is somehow related to the concept of programmable matter. In certain view, artificial intelligence and also embodied artificial intelligence can be viewed as a generalization concept of particle to a kind of cognitive particle concept. And then in particular, I would like to relate to classical neural networks and then make a kind of smooth transition to a quantum neural networks. So I will also have a need to mention basic facts about quantum mechanics, since quantum technologies and cannot be done without fundamental study of quantum mechanics. All right. So basically, right now there is a lot of developed technologies in classical artificial intelligence, and we have digital electronics very well developed. Basically, the existing electronics operates with use of sharp logic, which bases on usage of 0 and 1. And also, neural networks works in a framework of fuzzy logic. So we might have all continuous states between 0 and 1. However, those states are real valued. So so you can see the all, I would say, degrees of gray color, right? From if you go from black to white color. So in a sense, you can move on one path between two color intensities. So this is what happens with in classical electronics. And with quantum electronics, with quantum, you have a quantum logic, and quantum logic is about existence of qubit. So basically, you have your quantum state is a superposition of state, can be superposition of various states. In particular, it can be superposition of 0 and 1 state. So you have two mixing coefficients, alpha and beta. So you can also make such spinor representation or vector representation as shown here. And what is important is that alpha and beta are complex value numbers that are normalized. So you can write them in the following way. And what really matters is that you can parameterize alpha and beta by cosine theta, sine theta, and by occurrence of additional phase. So basically, you will have a phase difference between your 0 and 1, and also your qubit can have a global phase. So this basically extends your fuzzy logic concept to a so-called block sphere. So basically, this is visible here. So you have classical. So you have fuzzy logic, which is shown here, and then in a qubit, you have a block sphere of unit length, and basically you need two angles to describe the quantum state. So and then so there are like two angles essentially, and basically yeah. So in very particular case, you can if you go along 0 and 1 line, you can have fuzzy logic. But basically, qubit has much bigger information capacity than just classical bits or classical fuzzy bit, let's say. All right. So basically, using this concept, we can define the registers, so-called quantum registers, which will be a superposition of various type of states. And then we need to think about how to generalize the logical operations. So in classical logic, we have classical inverter, which inverts 0 to 1 and 1 to 0. But now you need to think in a framework of a block sphere. So you need to, yeah, so you can, if you reverse the 0 here, you will end up with 1 here. So you need to apply Pauli matrices. So you see the richness of inverter operation in quantum logic. Okay. You can also define many other operations, which is like you can define quantum Hadamard gate. It will be similar. So basically, the operation on the given 0 input gives you final output, which is a superposition 0 and 1, as given here. Basically, you can view the Hadamard. Yeah, so this is Hadamard. So it also changes 1 to 0 minus 1 over square root of 2. Then you can also define so-called controlled NOT gates. So basically the behavior will be that first bit is a controlling bit. So, and second bit is negated if controlling bit is 1. So if first controlling bit is 0, nothing changes. But if first controlling bit is 1, then you have inversion of 0 and 1. However, this is done in relation to a block sphere. So such gate is represented also in such way as given here. So Hadamard and CNOT gates and belong to a class of universal gates, and universal gates allows us to implement a quantum computer. Okay, so basically, since my time is quite limited, I will not mention about...
Chris, since we are recording the lecture, take your time. So I think we are happy to wait 15 minutes more.
All right. So basically, we should mention that that basically all information is physical. This is Landauer statement. But also noise is information. And basically, we need to view the computation process as evolution of a physical system with time, under certain constraints which are set by given technology. So of course, initially, the first computer was a mechanical computer. Then the electronics was implemented in transistors, and in particular in CMOS. So basically, you can say that all logical operations are just related to evolution of the physical system under given constraints. So basically, you set up physical system in the initial state. You set up certain registers, and then you let the system to evolve, which you can name it. You make a computation, and after a certain time of system evolution, your registers achieve certain values, and then you make so-called readout of this computation process. So basically, you determine what is the physical state of your registers after the physical evolution takes place. So this is the concept which is maybe which is valid both for classical and quantum computers. But of course, let's say in case of quantum computers, the act of measurement and the act brings additional challenges, and basically there are certain additional peculiar properties that are associated with quantum states. So basically, during readout, we destroy the wave function of a given system. So I will mention about this fact on the next slides. In any case, basically, all computers can be described by physics equations coming from physics, and we also face the problem of entropy. So so this concept of entropy, as you know, is incorporated from physics into information science. Okay, so basically, as to my understanding, the artificial intelligence can be seen as a concept of programmable matter. So basically, like you see, how would you recognize that aliens are coming to the Earth? There is a movie, Independence Day, where aliens, there was a black object coming to Earth, and it was slowing down the gravitational field of Earth, which is unnatural to objects without intelligence. So in a sense, intelligence can be seen also as a kind of violation of laws of physics. Well, this is not directly violation laws of physics, but it might look like. So basically, the concept, there's the presence of social force that exists in a generalized particle concept. So there is a motor system and sensor system. So basically, this can be seen as extension of laws of physics. And all robotic agents somehow are a manifestation of this concept of programmable matter. Maybe a very nice example, which I always like to see, is a concept of Breitenberg vehicles. And in particular, I like the work of Izuka and Takashi Kegami. So there is a Breitenberg vehicle with two sensors that are located here. There is certain range of sensors, certain range of space which can be perceived by sensors. And there is a force applied to left and right wheel. And this, if we place certain neural networks, recurrent neural networks into these agents, basically, and we subject these agents to artificial evolution, various trajectories can be achieved. Right? So I would say, if you use tools of statistical physics, you can see this evolution as a kind of extension, certain laws of physics from certain perspective, of course. So this is what I call the concept of programmable matter. Basically, yes, this embodied artificial intelligence is about emergence of certain properties of this programmable matter under this evolution, and that is done in interaction with environment. Okay, so having such definition, now we can move further with into the concept of quantum intelligence. So basically now we need to think that this kind of robotic agents are kind of could be like quantum particles that moves in some effective fields. For example, we can think in that way. But before doing it, I will simply revise the concept of classical neural network. So as you know, the neural networks has very big power in interpolating the reality around us. So we can recognize voice as image. We can also represent certain algorithms by some internal dynamics of artificial neural networks. But anyway, the concept of neural network is quite simple. So we have certain inputs, we have certain weight, which is about the connection's weight, and there's certain nonlinear function that is applied to this, so F. Sometimes we have also biasing signal B. So basically we can apply various type of nonlinear functions, F. And so this is basically the basic concept of classical neural network. Now there is a question how to come from classical neural network into quantum neural network. That is my main, one of my main research interests right now. Okay, before doing it, I need to move back to basic laws of physics. So as I stated before, the cognitive agent, robotic agents can be seen as extension of laws of physics, like if we add this social force concept, for example. So now we ask what is the quantum physics and what is additional features coming from quantum physics picture. So basically, we need to understand that all measured quantities are observables, and then there is a dualism, particle wave dualism, that is shown by all particles at certain nanoscales. So basically, the state of particle is described by a wave function C, and there are operators which are observables acting on a given wave function. So we have a kinetic energy operator is of this form. There is potential energy and there is a total energy of a system. So this is like Schrödinger equation is nothing else as manifestation of conservation of energy in an isolated system. So sum of kinetic and potential energy must be constant. But the essential difference is that the solution of this equation is a density of probability of particle occupancy. So essentially, if you place the particle in a box with infinite walls, what you will see, you will see that there are certain modes for this C wave function, and this modes, this is like ground mode, first excited mode, second excited mode, and so on. These modes give you discrete spectrum of energies and gives you certain density of probability of particle occupancy. So you no longer deal with kind of classical determinism. So you need to think in this picture. So basically, square modulus of C, which is complex value function, is a density of probability. All right. So and there is also possibility of coexistence of few states at the same time if the quantum system is not being observed by external observator, let's say, when the act of measurement is not done. However, if you do the act of measurement, you can reduce, so the system can have can be superposition of three different eigenenergies. Once the observation is done, certain eigenenergies shown to the measurement apparatus, and the initial wave function collapses into one of these superpositions. And there's another issue related with this with quantum mechanics, which is non-locality. There's a very peculiar correlation between two particles known as a quantum entanglement. So essentially you have this system before the measurement. This is like a Bell state system, which is shown here. After the measurement, the system collapses. And if you determine that the spin of the first particle is spin up, this gives you immediately the spin of another particle. And this is known as a spooky action on the distance. So if your wave function is spread between Moon and Earth, if you act on this wave function with an act of measurement, you can back of measurement you can impose the state of particle on the Moon being on the Earth, and this is already done. So like Chinese built first a quantum satellite that shows certain entanglement with Earth station. All right, so this was very briefly about quantum entanglement concepts. And right now there is richness of development of quantum technologies. The idea is that basically the quantum system is a superposition so quantum state can be superposition of various states. And if you leave the system alone, the system will evolve on all possible paths. There is certain massive parallelism present in a quantum computer. And this gives you certain supremacy of the quantum computer over classical computer. But in order to achieve this supremacy, we need to be able to implement the qubit in hardware. And recently, there are at least 5 different main schemes of implementation of a quantum computer. So basically, people are dealing with superconducting Josephson junctions. So big players like Google, IBM, Intel, and so on. Also, Microsoft is using topological Josephson junctions. Then we have ion traps and various other implementation as silicon quantum dots or diamond vacancies. I will not describe these technologies in details. I am just mentioning that right now there is a race towards implementation of a quantum computer, and this quantum computer can also represent you a certain level of quantum intelligence. All right, so just to make a brief summary of the key features of quantum mechanics and quantum technologies. So basically, there is massive parallelism of processes taking place, and such parallelism is non-existing in classical physics, in classical electronics. However, your quantum state is very fragile against all other perturbations. So usually these quantum computers are very expensive. They operate in the range of temperatures of 15 millikelvin. So they need the usage. There's a use of dilution refrigerator, helium-4, helium-3 mixture. So there's no such thing as sharp trajectory of evolution of the quantum state. There are various possibilities related to quantum metrology. So basically, you can build the most sensitive detectors using qubits, for example, and then you can integrate this with electronic devices. So I would say your perception of the reality by a quantum chip could be even better than by classical silicon chip. There are other issues related to quantum features. One of these is no cloning theorem. So you cannot clone exactly the existing qubits, and neither you cannot fully delete its state. So there's always it is somehow remembered by global system Hamiltonian and global system state. So there is certain quantization of physical quantities as it is expressed by Schrödinger equation, and very much what is really essential in quantum computation is non-locality. So this is non-local correlation that can be propagated over big distances with speed higher than the speed of light. This doesn't still violate the Einstein relativistic theory, but this non-locality is strongly used in a quantum computer. One of manifestations of non-locality is of occurrence of teleportation. So if Alice and Bob are sharing the same entangled state, once the Bob determines the state of first particle, then it can communicate to Alice that what is the state of the second particle because it's immediately affected. Then all right. So basically, the history of quantum computation starts from Feynman ideas from 80s, and initial concept was to build a quantum system that can map the dynamics of various types of quantum systems. Later, it was shown that quantum Turing machine can represent classical Turing machine, but it has much bigger computation possibilities. In particular case, it was shown that Shor algorithm can factorize very big number with polynomial complexity, not with exponential complexity as it is in case of classical computer. So later it was shown that that quantum computation can have its supremacy over classical computation. In particular case, it was shown that there is implementation of extension of classical game theory into quantum game theories, quantum strategies. And recently, there is development of a new field, which is the quantum artificial life. Actually, quite recently, IBM claims to achieve preliminary artificial life systems implementation in Josephson junction circuits. Okay, so it was very brief. So basically, now I'm moving to the concept of a quantum neural network. So basically, we need to be aware how to generalize the classical neural network. So essentially, our inputs will not be scalar value functions, not real value functions, but our input will be a set of n qubits that could be entangled or non-entangled. And so the neural network performs certain evolution of the systems with time, and the output of neural network is again the state of qubits. So there is a certain number of qubits, and also these qubits can be also correlated. It can be also correlated in non-classical way. Okay, and now we need to think how to implement the neural network, how to set the weights on. So what's the value of connections? What's the weight assigned to a given connection? How we can represent it in relation to a wave function? Okay, so basically, maybe at first I will show it. So basically, one of possibilities is to implement a neural network, quantum neural network, in a chain of coupled quantum dots. So we can have, for example, 3 qubits, and we can apply certain voltage to gates between quantum dots. That way, we can control how the quantum dots are interacting. So basically, we can set certain wave functions as input of this neural network, of this quantum neural network. Then it's quite naturally that the wave function can be partly transmitted and partly reflected. So in a such way, you can implement these weights. But basically, the system is, I would say, the dynamics of the system is nothing else as quantum dynamics. As a quantum dynamics that is controlled by the signal applied to the gates. That's how it is. All right. So, and then you can think how to learn the quantum neural networks. Well, you can randomly choose the potential, the biasing potential that is given to gray gates, and then you can this 3 input 3 output neural network can implement, for example, quantum universal gates, or can implement quantum logical operations. But how to be able to correct or to evaluate the performance of the neural network, quantum neural network? Well, we need to use the concept of fidelity. So the neural network will give you certain state of qubits as output. And of course, so, there is nothing like perfect neural network. So there's always some mistake, some randomness and some mistake present in output of neural network. However, we need to know how far we are from ideal situation. And then we need to introduce the concept of fidelity. So fidelity is a concept that can describe you how one quantum state is far away from another quantum state. So it's essentially, if you have 2 random variables x and y, and there is a certain probabilities of occurrence of x and y, then fidelity is defined in such a way. So if probabilities pi and qi are the same, this sum will give you essentially 1. So in a sense, so then 2 states will be the same. Then you need to apply this concept of fidelity to a quantum system, and there is more general way of describing the quantum system than a usage of a wave function. So essentially, we use the concept of so-called density matrix. Density matrix is a Hermitian matrix, and then we apply trace operation, which is the sum of all its elements on its diagonal. Basically, for 2 density matrices as given here, there, you can define the fidelity, which is expressed by this formula. It looks a little bit horrific, nevertheless, this fidelity can be used to express how the output of neural network is far away from ideal output, which you want to have. And so in that sense, you can define the learning function. All right. So basically, maybe one more thing. So I have shown very simply the concept of the quantum neural network, how it can be implemented. So obviously the quantum neural network, because of certain non-local correlations, has the capacity to simulate classical neural network, and more, it can also, it has certain superiority over classical neural network. Maybe very briefly, another example of supremacy of a quantum computer over classical computer is expressed by various types of algorithms. One of the simplest algorithms that you can imagine is a classical and quantum annealing. So annealing is about finding the global minimum energy. And usually you can have various types of potential, and they basically, by activating particles that are thermally the particles, and sooner or later the particles will find its global minimum. However, in case of quantum annealing, this process has certain speed up, because once the particle lands you in local energy minima, there will be certain non-zero tunneling possibility, and this tunneling will speed up the algorithm performance. So actually, D-Wave company claims to implement the quantum annealing with 2,000 Josephson junction qubits. All right. So basically, So I would say the dynamics of quantum neural network is also an example of many-body physics. Maybe I will not go into details. So this is about solutions of Schrödinger equation. Maybe I would just end up. There's some nice analogies between classical and classical neural networks and the quantum mechanics. So yeah. So basically, this superposition has to do with interconnections of neural network. And we have instead of we have wave functions implementing our neuron. So probably this certain analogies can be drawn even more deeper if we make some analogy between classical statistical physics and quantum physics. All right, so basically these are the most basic issues described by me. So basically, if one is more interested in the subject, please contact me directly, and I can give some extra references, or we can conduct deeper discussions. All right. So there is a richness of topics related with quantum artificial intelligence. So basically, like all bigger commercial entities as Google, IBM are working on this field, and this is now a very hot topic. So I would say there was certain era of development of artificial intelligence and artificial life, and I would say now it's a kind of golden age for quantum artificial intelligence. Right? That's at least that's my perception. All right. Thank you.
Thank you for this very interesting presentation. As you see, I think there is some, because I unmuted everybody to allow the questions, but it seems that there is some echo. Okay, so we have. So thank you. I think it's a very interesting thing because presentation, because you see, we were talking about clocks as a support for computing. Now we use sometimes without even understanding what's going on electronic computers but in principle any physical process can be used for computing. And I think you got the idea from Chris was saying that quantum systems are a very attractive platform. And then, of course, it remains open about if our brain uses quantum computing or not, if it is necessary or not. By the way, I'd like to know what you think about it.
All right, so basically, unfortunately, one of my grant proposals was rejected. It was about implementation of a classical quantum mind in a superconductor. So basically, now there is development of rapid single quantum flux electronics that implements very effectively classical electronics in Josephson junction physics. At the same time, you have development of quantum bits in Josephson junction physics. Josephson junctions. However, always the quantum systems are more expensive. So, but basically, you can combine both of them. I would say, and what is very remarkable that there is certain spiking behavior that can be very easily mimicked by Josephson junction systems. So I would say we have now the power to implement hybrid quantum classical mind in Josephson junction systems, and we can test various hypotheses. Of course, I'm sure many people here are familiar with Schrödinger ideas that we have a kind of Bose-Einstein condensate hidden in our brain, but still this hypothesis is very hardly to be tested. So I would say biological system is a nightmare to test such type of hypothesis. What I would suggest is instead of doing like a kind of very difficult task, we could rather build a new system that has the power to mimic our brain. And right now it seems to me that Josephson junctions are a good candidate for a hybrid classical quantum computer. So this is one thing. However, right now I'm working at UCD on semiconductor CMOS qubits. And so we are developing the chip. We want to implement 62 qubits, and we want to develop the quantum computer that has scalability properties. So I believe I somewhat answered on your question, right?
Yeah, yeah. Of course, it will take some time to have a real answer, but I mean, the work of many people. So thank you for this very interesting and inspiring lecture. I don't know if there are questions from the audience. Maybe it's a bit late, but I'm sure that Christoph will be happy to answer privately to any question you may have. And so thank you, everybody. I don't see any hand raising. So thank you, everybody, and see you next time. Thank you.